I'm Brian Kempa with the Intelligent Systems Division at NASA Ames. I'm currently serving as flight software lead for the Distributed Spacecraft Autonomy Group, among other hats. And the Dr. Strangelove title of this talk could easily be How I Learned to Stop Worrying and Love Containers. This is a talk about some of the fringe benefits. I use benefits somewhat in scare quotes, side activities, kind of loose bits of tech that we accumulated while we were working on our mainline projects and how we tried to turn those into actual deliverable results or how they helped us further down the line. This is not a like we did this and therefore you should too this way lessons learned style presentation. This is a let's look at the reality of what happens when you start executing a project and you get hit with budget changes and organizational shifts and someone hands you a board that just absolutely refuses to boot for a month and how you can try to spin that to your own benefit later on. So a quick overview of my background so you can properly adjust for the measurement signal that I'm giving you. My background's in aerospace engineering, although I did a lot of graduate research in formal methods, so I'm forever fighting the good fight that software engineering currently doesn't have the same level of formal rigor of will this bridge collapse. Despite that, I'm truly an engineer. I want to fly things in space. I'm not going to sit around and wait until the proofs, fully close. And despite being a relatively junior staff member, I've had the great fortune of being able to touch flight software from Class A Gateway through Viper Lunar Rover. I've seen a wide variety of classes, and everything I'm talking about today is low TRL tech dev. Do not put any of this into production. But it's how we get the experience that we roll into those higher class missions. So I'm going to start with the more controversial of the two frameworks we're going to use to define DSA. This is the jawbreaker. Obviously, this is going to be a lot more problematic to discuss than the pentagram that is coming up. So this is the set of all space missions. And within that, you can have multi-spacecraft systems. Multi-spacecraft systems are becoming more prevalent as launch costs are going down, and we want simultaneous spatio-temporal measurements and all these other great things. And sometimes your space missions require autonomy. Autonomy versus automation is a debate we should totally have over coffee at some point. But right now, we're interested in the center part of these two sets. So I will clean that up a bit with some terrible PowerPoint animation. And we get the autonomous multi-spacecraft systems. This is where you really start having a fun time with the high-level, complex cyber-physical system, V&V. You start breaking down some of the assumptions that your traditional methods of engineering trust would use. And further within that is what my group at NASA Ames is really focused on right now, distributed space systems. We define this very specifically as you are not using any of the traditional distributed systems literature techniques to pretend that you're centralized. We're not going to do leader election and wait all day for consensus to occur, either because we don't need that or we can't afford it. What do you do in those cases? And it turns out there are cases where that is more interesting or more valuable, and there's definitely cases you should not use this. Now, the pentagram I oversold, it's a pentagon that I stole from DARPA, specifically the offset program. This is how we look at the ways that we can scale this complexity in these systems. Just moving around clockwise from the top, you can increase the number, you can increase the complexity of the total objective. There's the human swarm interaction component. We've had some mentions of that throughout this conference. That is very interesting, and I'm not going to touch it at all today. This is flight software, not the ground systems. There's better people for that than me. Heterogeneity, of course, and the individual complexity of the agent. The DSA project is focused on those three in particular, and our recently completed orbital demonstration on the Starling 1.0 CubeSats fits in very neatly into that little center slice of this pentagon. So for anyone who hasn't seen the NASA Starling mission, this is a set of 4 CubeSats built by Blue Canyon that do a number of distributed autonomy and general swarm capability technology demonstrations. This is an artist's rendition of what the DSA payload itself looks like in operation. We are using ionospheric anomalies as a science proxy. We are not doing real science. We were talking with real scientists about how to turn this into real science, but we just needed a measurement that we could react off of. And the swarm measures the ionospheric, effectively, it takes a path integral of the electrons between itself and all the GPS satellites it can see. It's looking for unexpected or interesting ionospheric phenomenon. And they gossip with each other about what they're seeing and determine where to turn selective attention. This is a measurement selection problem. This is not the most interesting, but it is the most fundamental form of this sort of distributed autonomy. Every agent is not like asking, what do you think I should do? Or coordinating on what they think they should do. Every agent is sharing, this is what I'm seeing in the world, and individually from their picture of what they know, they're deciding, this is not only the best for me, but this is what would be the best for everyone, and I'm gonna do my part in that. And that gives us some interesting robustness, behavior, and trade-offs. This is my scariest slide because these are some very bold claims for first, but I promise people much smarter than me have tuned these very carefully. The distributed in front of autonomy there is load bearing. We have run this by a number of people who would have reasonable claims to these points if you were to slightly reword them. And we even sent our mission ops lead down to JPL with this slide, and they returned him in one piece. So I'm fairly confident presenting it to you today. This is great. These are, fun sounding things, but that's not what I'm here to talk about today. I'm here to talk about what happened when we actually tried to build this thing, the trials and tribulations of running a real project. At the end of the day, to do that demo, we just had to make 3 apps. This maps neatly to your Sense Plan Act model. The TEC app actually produces the measurement out of the GPS signals. The communications app is what allows the satellites to gossip with each other. We use a combination of DDS over a layer 2 cross-link mesh network. So they just constantly are sending out, here's what I'm seeing, what are you seeing? They take what they can. If there's a delay, if there's a partition, if there's a drop, they don't care. They can keep on rolling. And it all goes into the autonomy app, which we very proudly wrote to actually build and then solve an MILP every cycle. We're not running a pre-built model. We are actually building the model up from scratch based off the world information every time. And we did not just hard code a solution to our specific problem. We're running a general purpose solver that'll come up later. So to build those 3 apps, we built this terrible infrastructure, which no one can or should do if they're just told, here is X dollars, go build these 3 apps, you're going to space in N years. Everything on this slide happened for a reason, as I'm sure you're all familiar with. Every technology is a path function of how it was created. And we have things in here that only exist because of organizational security requirements, or because we had the bus vendor change partway through and we weren't involved in that decision making because of the way the project was split between the Starling main team and the DSA team. There's IT considerations in here. You see that we have a developer environment configuration at the top left there, and we build both containers and develop common developer VMs off of that. So we can, regardless of who's got an M3 Mac versus an Intel chipset Linux machine versus, oh, we have to run this one on the server, and that OS is the latest FIPS certified version, which means it doesn't run a version of CMake new enough to understand our build system. We don't care about any of that. We package it all up in there. Yes, it's overhead, but it's overhead that we would rather put in this box and have 1 or 2 people worry about occasionally than deal with moment to moment, day to day when your platform changes. I'm not going to walk through all of this. I'm going to walk through the consequences of having built this and how this actually became a positive for us. The first positive, in the way that we sell it to the people who actually provide us our money in the program office, is this was what the build configuration test and validation chart looked like when we were just running with what we were given. And this is what it looked like after we spent, it was about 2 months building out that terrible automated infrastructure system. From the empirical measurement of how many lines and boxes do you have, this is significantly better, and so we moved on. A core piece of this was the push button get swarm system. This was proudly an intern project one summer. We needed to start having individual developers see the collective and emergent behavior of those systems on their laptops as they were making the changes. So we sent them off to do a trade study, and I said, containers are great, please run anything other than Docker, because I had been burned before, and they did a fantastic trade study and came back and said, we're using Docker and you're going to love it. but it's great. I mean, I just used this yesterday for, in preparation for a command load. You can run one command and it'll spin up 4 spacecraft. We can condition the network between them. We can say, okay, insert a partition, here's your loss rate, whatever, whatever, and everyone can see on their laptop whether you're running in a container itself, you have a developer VM, you're pushing it off to one of our project servers for more power. And this is inextricably tied to how we built our testing system. Another point of reality was the version of CFS that our upstream mission was using did not have a functional test suite. The version after it was functional, but we couldn't backport it, and the version before was functional and it was not did not play nicely, and that's what we were stuck with. And so we built our own collection of Google test harnesses to take advantage of developers we were getting into the project who were not flight software devs, but were very experienced C++ developers. And so making lemonade out of the lemons we were handed, we have 3 levels of testing and they build on each other. So as we built each level up, we reuse the vast majority of the code from the prior level and it reduces our maintenance version. And that goes all the way to the swarm testing for the push button get swarm, where you can spin up multiple nodes, connect them together arbitrarily and see the behavior. But we took that a step further and tied it into our higher level, higher fidelity levels of testing. We now have a full scenario runner where we run on a dev machine all your telemetry input and output, and you run the conditioned network, and you can see how the swarm will behave on orbit on a single laptop. And this has almost no changes. We're going to move a line and the image of the laptop over to the kind of low fidelity hardware, developer hardware that we all had on our desks, up to the higher fidelity hardware in the lab. And the fact that our testing was consistent, we weren't messing with, oh, new test harness, new test configuration, whatever from stage to stage. You could run your unit tests from a developer laptop on the flight hardware. It was all seamless. So that paid off for us well just in the Starling mission, but we just didn't do a demo for satellites because n equals 4, you can hard code that. No one's really impressed. I mean, I'm impressed. My grandmother's very impressed. It ran in space. But to impress the program office and convince them that with their money, we actually did write a reusable autonomy stack and not a one-off tech demo, we did a ground scalability study of a lunar position navigation and timing case. And you can see how that affects the Pentagon here. We're working with the swarm as a single unit from the operator's perspective. We're increasing the collective complexity of the system, and we're scaling up to 100 spacecraft. So the PNT, the lunar PNT system has been published elsewhere. You can look into it. It is a benchmark problem set. No one is suggesting this is how you should actually run a lunar PNT system. We know many people working on that problem who have better ideas. But we imagined a future where you have 20 to 100 other missions already at the moon, and they have they have agreed to carry a little transponder that gets a tiny sliver of power in time and has to cooperatively provide positioning services to the ground with that. The way that ends up working is the spacecraft does 2 phases of that gossip communication. One is they form a Hamiltonian path. You get a nice big ring. They shift all their state information around about where they think and know they are. Then they use that information to do a stable matching problem and say, okay, based off my knowledge of my clock drift and my position uncertainty, who's the best person I could do a radar range with and really clamp that down? And the whole swarm computes their best matches, and then they slew and point at each other, take that measurement and propagate the Kalman filter. Looking at how that looks in terms of the actual apps, we went from these 3 apps to these 4. The COM app stayed exactly the same. The TEC became a DEKF. You had to have someone write a good Kalman filter, which is non-trivial, but that's application specific. The MPlan and Net apps, though, those are just the auto app with a different problem statement. The core code is the same. And so the fact that we were able to take multiple instances of the problem, change the description, and run an entirely different use case, we saw that as proof that we were building a more general technology. And we decided to make it painful ourselves, as someone said earlier this week, simulations being doomed to succeed. We decided to run it all on hardware. So this is the DIST track, getting an acronymed DIST track, Distributed Intelligent Spacecraft Simulation Test Track, was originally a threat from me to our PM to come up with a better name before we published, and then it became, I'm pretty sure the justification for my civil service position was the ability to make an acronym that terrible. we used a set of, so I said heterogeneity was out of scope for us, but we did run this on a variety of different hardware just to show that we can tackle architectures that are kind of current, future looking, some things that were in the recent past, et cetera. And the fun part was looking back at push button get swarm and the way that the disk track works, you may notice that we just reused 90% of that test code. So now we have a contiguous test interface and infrastructure going back from, hey, the board vendor changed. You have to run a completely different architecture and it's incompatible with all your hardware systems. What we were forced to do with that was now allowing us to run these 100 processor in the loop tests in the lab down the hall. So that has been very valuable for us. No one would sit down and say you should do any one of these things. And I would tell you, if you have the, the foresight to do so, you should not do anything like this. But being forced to, we were able to leverage that to our benefit. Results of this are published elsewhere, but this is a fun little graphic. This is the 21 node case. You can see how the satellites pick in red which measurements they're going to take with each other out of all the possible ones. And the service is not great. It's a benchmark problem. It's not designed to be great, but there's some interesting robustness characteristics that was just published at the Institute of Navigation International Technical Meeting. We have a different set of off-nominal behavior we're looking at for ascend, and this has been very valuable for us to see what happens in different failure cases, what happens when your network is really inconsistent, what happens when you're consistent but delayed. Having a benchmark problem to study those impacts on has been great to validate the theory. We don't have time to talk about space, Ross. I started programming 8-bit flight controllers in assembly. So this high-level stuff has always been, I've been very skeptical of it, but I'm on the Space ROS maintainer group because it'd be great to reuse a lot of that. And importantly, that same tech we used for all those testing meant that we were able to use the DSA applications, the Starling version, as a Space ROS benchmark in an afternoon of effort. We swapped out the send CFS DDS conversion message function with a write to Space ROS bus message, and everything just worked. Okay, so from my favorite acronym to my least favorite acronym, I'm going to blame my project manager for this one because he put it in as a placeholder and did not change it before he got it funded because, no one's going to complain about getting something funded, but we would have liked to take a second pass at OSESAT, Opportunistic Software Experiments for Satellite Autonomy Testbeds. This was a short turnaround flight opportunity. Someone said, hey, we have some extra processor cycles. Would you like to throw your tech in space? We said, we have neither the time nor the money to do this, but we have some containers sitting around, and if you want to just fly those for us, that would be great. So why not fly your test harness? Not only was this successful, but we have now spun this around into a outward-facing collaborative project that sounds very similar to both a number of commercial offerings and a number of efforts that we've heard of this week that are much better. You should look at something like that for serious work, but the fact that we can take effectively the scraps, the trimmings of our technical effort and turn them into their own technical contributions and their own technical pathfinding has been enormously beneficial. This is the one joke of the presentation. I hope you have all seen this. And the way this looks for us is we are presuming someone is providing container services. There's commercial partners that do this. We are running this on the R5 satellite coming up, one of the R5 missions coming out of JSC here soon. And they just say, we'll give you Docker. We're going to give you a trusted container. This is a traditionally flight software engineered, validated program. And then that trusted container spins up and runs and monitors and kills and gatekeeps all these experimental containers. I have lost track of my available time, so we're going to skip forward. We have run some of these. We are about to run others. It has been incredibly tight turnaround. We were able to go from, hey, this R5 thing exists, to working with a team at Goddard to run their AI experiments through OSESAT containers on the R5 satellite in just under 2 months, with one person working part-time on it from the Ames side and some additional effort at the JSC and Goddard side, of course. Hope to have results at SmallSat. So containers for flight software, I am a big skeptic, but I can't say that they didn't pay off for us in spades. In just the ability to reuse that technical effort we were already putting in and make these other opportunities. Not only could we say, yeah, we'll take that quick turnaround 3-month flight opportunity, but we can bring in 2 other groups and all play nice together in that sandbox. To misquote the apocryphal machine learning is usually the second best option. I've found containers are frequently the second best option, but in reality, when you're working with the third or the nth best option, why not jump up to the second? It really helped us paper over the programmatic challenges, budget, tech, staff. This is not something you would do in a clean sheet, and that's okay because the world is not a clean sheet design. Yeah, so not magic, not a replacement for engineering development units, I say, because we had a couple of those projects work without real good engineering development units and we paid for it, but it got us most of the way there. And moving forward, we're working on integrating this with more types of flight software. This is not like, hey, please come use our stuff. This is, hey, let's talk about what actually happened when you went to execute your project and how can you keep making the lemonade out of those lemons. If you want to talk about the meat and potatoes of the technical work behind it and not just the infrastructure side, you should come talk to us at the Distributed Autonomy for Space Systems Workshop. I will yield my time there.
Thank you. Question?
Great talk. You had a slide on push button get swarm, and I was curious, did you ever try doing that locally for the lunar PNT option where you had like 100 containers? So you had it working with 4 containers on someone's desktop, but did you scale up to 100 and was that successful?
I don't think we ran 100 on a laptop, but we have run the 20 case on a laptop, and a couple of our former interns did a lot of study on which network stacks and configurations can expect which throughput. So we have a little calculator that'll tell you basically with this CFS configuration, the expected message volume, you can run it here or it's not going to work on your machine, push it to the project server. But we also invested in a beefy project server, so that is always available to people.
Hey, thanks for the chat. Sort of 2 questions, but one's a really easy one. The first one is, did you build your own containers or did you just have someone pull down Ubuntu or, because people just use containers all sorts of ways. Did you have a structured way that you used them? And the second part is, did you investigate fault tolerance by the use of multiple containers or at all?
Yeah, I'm going to take the second part first and work backwards. So the OSC SAT experiment, the first one, hey, someone has space in 3 months, that was a basic TMR voting between containers with intentional corruption because we only had a single node. And now we're scaling out to what it looks like applying the DSA stack if you have multiple nodes. So that's actually where we started with that. And we like it because it lets us fly lower TRL, lower validated software and put all our eggs in the basket of that trusted container uses, runtime verification, some other fancy stuff to say, okay, if you can trust that, if you can fuzz this container and prove that it's not going to blow up your flight stack, and therefore you can put anything behind it and not care. And then going back to the Docker file itself, that's where I stepped into the trade space of, well, if we're using Docker, I'm going to get some not invented here syndrome in here. And we wrote like the bare container that copied out from 6 layers, so it built really fast. And that was fun, but not necessary. It was a great technical learning experience for us, but for this stack to work, we can also just run the base ones. And we have, when we didn't have time, when we needed a quick experiment, and we went back and cleaned it up later to keep the CI pipeline moving fast. So
We can take another one. Yeah.
Thank you, Brian. Excellent talk. Your physical systems are going to become heterogeneous in flight. Radiation, grease on a reaction wheel changing. How are you treating? Have you worked on methods to? I know you left it out. I remember the pentagon, right? So you made a pentagon a square. But
So
go ahead. Thank you.
those types of things are mostly handled at this level by changing That relay app is our bit of cheat towards flight realisticness. It lets us do some bust injection on the target so we can say, okay, you're getting bad GPS messages. We can pre-compute that one of them is producing bad telemetry. So we can do those kinds of the realistic off nominal in this configuration.
I think we are out of time, but Michael Monahan is giving a shout out that Goddard experiment team is watching you. So